The concept of bionic, I'm sure you've heard this word before. For example, the 70s show Bionic Woman. Usually what it refers to, especially for mechanical engineers like myself, it usually refers to people who are trying to make robots, which are kind of mechanical systems, behave more and more like humans. But what if you could actually invert that idea and do the opposite? What if you could actually take humans and make them more and more robot-like, so that way they can compete with the robots in the future? How do you do that? And it turns out from a materials perspective, it's actually a pretty interesting problem. And it's an interesting problem from a number of different perspectives. It's not science fiction because there are actually cyborgs among us today. For example, there's people who wear cochlear implants, people who wear pacemakers. So these are devices, electronic devices that are fully interwoven into someone's body. And the point of these devices is typically to restore impaired capabilities. For example, you lose your hearing, so you need to have one of these cochlear implants to restore your hearing. Or you have impaired heart functionality, so you need a pacemaker to jumpstart the heart every once in a while. So that makes a lot of biomedical sense. It's a really exciting area. And the question that we ask as material scientists is, we span the gamut. So from at one level, how does one actually tailor electronic systems so they're more invisible, so they're better interwoven into the body rather than kind of these devices which you can clearly see, for example, in this case for the cochlear implant on the side of the head. But from another perspective, you can ask the question, well, can these devices be used for regenerative purposes? Or even more interestingly, can you have human-machine interfaces so that you can actually give humans augmented functionality over what they would ordinarily have by interfacing these devices with the body? And it turns out, again, it's not science fiction. I'll explain that later. But when I was in college, it took us about 3 round trips to get my computer into the dorm. But these days, you can basically have this entire computer basically that you can put in your pocket. So in one sense, these cell phones are pretty amazing devices in the sense that you can actually take this computing power, put it in your pocket. But you can also think of these cell phones as these big, bulky devices that you have to carry around with you. What if you could just interface it directly with the body so you don't have to worry about it? And from a materials perspective, this is an interesting problem because of the fact that there's 3 issues here. Why can't you do that? Why don't you have electronics fully interwoven into the biology? And the first reason has to do with the fact that biology is soft, flexible, stretchable, whereas electronics are hard and rigid. So the mechanics are completely different. The second thing has to do with the fact that the electronic materials require high temperatures to process, which are much higher than what biology can handle. And then the third reason is if you look at your cell phone, it's pretty much a 2-dimensional flat device, whereas biology is 3-dimensional. So we ask as material scientists, how do you overcome these issues here? And the way that we do it is we use nanomaterials in order to do that, because nanoscale materials, they have different mechanical properties, different electronic properties that allow them to be more easily interfaced or even interwoven into the biology. So I'll explain a couple projects where we've done this. For example, I think the simplest type of idea is what if you could have electronic material that's already kind of tissue-like. So we've worked with materials like graphene. These are 4 spots of graphene that have been printed onto a silk, which is a water-soluble substrate. So you can basically take this graphene on the silk, dissolve away the silk, and like a kid's temporary tattoo, you can leave the electronic material, the graphene, behind on the surface of the biology. For example, this case, a tooth, but you can also print it onto anything. You can print it onto, this is a big device, so we used a cow tooth. I'll explain the reasons for that afterwards if you'd like to. But anyway, you can put it onto hospital equipment. You can put it onto food like cheese, or you can even put it onto your skin. So this is an electronic tattoo where you have the electronics that are more tissue-like, and then they're merged onto the biology as a final step. So this is a way of overcoming these issues, getting electronics directly on the biology. But there's also some drawbacks to this approach. Specifically, this is still a 2-dimensional interfacing, and it's done at a final stage of the process. You have the biology here, electronics here, they're merged at the end. So one of the questions that we asked, and this movie won't play, but you can find this clip on YouTube. It's a movie of the Bionic Woman with her bionic hearing. One of the questions we asked ourselves is there actually a way to give a human augmented functionality? How do you do that? And how do you do this from a materials perspective? Instead of merging the biology and electronics as a final stage, can you actually grow the biology from scratch so that it has electronics interwoven into it? So the way that we did this is we created this idea of, can you print an organ from scratch that has fully interwoven electronics? This is a bionic ear that we made. And the way that we made it is we used a 3D printer. And most people know that 3D printers can be used to print plastic things like jewelry and other types of things like that. But we decided, can you take these 3D printers and hijack them and put functional materials into them? Can you put biology into them? Can you put nanoparticles into them so they have conducting properties? And we did, using this concept, we actually printed out a bionic ear that has all the components interwoven. So if you look at this ear, it is actual real cartilage tissue. We culture it in a petri dish. We use real live cells that get cultured into cartilage tissue. And you can see there that there's an electronic coil built into this ear. And basically what that does is, if you look at this coil here, it's actually on the surface of the ear, and all the cells around that coil are actually alive. That's what the green means. It means they're healthy cells that exist around this coil in the ear. And the coil is there on the surface of the ear, but then what it does, as you can see in the right image, is that it penetrates down vertically through the ear, and then it comes out through this kind of cochlear-shaped electrode on the side. So this is kind of like a cochlear implant plus a ear built into one, the biology electronics fully interwoven into one another. And it gives this ear, it's not just a piece of cartilage sitting on a table, but it actually gives the ear electronic functionality that it wouldn't ordinarily have. For example, these ears, on the one hand, they can do things that our ears can't do. So our ears are basically mechanical receptive devices. You have pressure waves that come, and they hear acoustic sound. So you have these pressure waves come, you have little hair cells in your ear, they vibrate at specific frequencies, and that converts the pressure waves that are coming at us into electrical signals that then go to your brain. So your brain is a purely electrical organ. But if you think about it, none of your 5 senses, and you've probably never thought about this before, but it turns out none of your 5 senses are electrical. For example, sight, you actually have photons come hit the eye, and it converts those photons into electrons that then go to your brain. Taste and smell are both chemical receptors that then get converted to electrical, go to the brain. And then touch and hearing are both pretty much mechanical sensory systems that then get converted to electrical, go to the brain. And the reason for that is because when we evolved in a world where we had to see fruit and smell food or hear lions that were about to attack us. So these 5 senses that we have are built on the fact that this is the world that we evolved in. But of course, this is not the world we live in today. And whenever I teach my class, my students are always not looking at me, but always looking at their cell phones. So we live in a world where we're kind of surrounded by electrical devices now. What if you could actually have a 6th sense capability that allows you to have direct communication with these electrical devices? For example, this ear here can hear in the normal range of hearing, but it can also hear up to the gigahertz range, and it picks up electromagnetic signals. And if you go to our YouTube page, you can actually listen to these ears listening to Beethoven. It was easy to get the license for that because Beethoven is dead, so it's free license. So these ears can listen to music, but they pick up sounds directly. So your cell phone now is an electronic device, but it has a speaker built into it to convert that electronic to mechanical. Then your ear converts that mechanical to electrical. And basically the argument that we're making is we can just skip the middleman and just have direct electrical communication with your cell phone. And again, it sounds like science fiction, but I've met people who wear cochlear implants, and they say they can actually take their iPhone, plug it directly into the implant, so the person next to them can't hear anything that's going on, but the person who's wearing the cochlear implant can actually hear everything perfectly, even though there's no actual acoustic signal processing going along, because you have the iPhone being directly connected to the cochlea, which then goes directly to the brain. And this is where I kind of see things going. Maybe it sounds a little bit scary, but I think 20 years ago, I think it would be scary to have electronics in your pocket, and that's the way things are now. So it's just a natural progression of things. And I think there's a lot of exciting things we can do in this area, both in the biomedical standpoint and in terms of augmenting human functionality. And I think another interesting question is, every technology has an early adopter. Who's the early adopter for this technology? And I think it's going to be the people who actually have the impaired functionality now, who are the early adopters who become bionic humans in the future.